Hi, don't forget to subscribe so you don't miss new videos. Sweet dreams! The industrial synthesis of high-precision steel ball bearings begins with the rigorous procurement of specialized raw materials, specifically high-carbon chromium steel, which is globally recognized under the technical designation of 52100. This particular metallurgical alloy is selected for its exceptional capacity to achieve high hardness, deep hardenability, and superior resistance to rolling contact fatigue. The chemical constitution of this substrate typically includes approximately 1% carbon and 1.5% chromium, along with trace amounts of manganese, silicon, and molybdenum. These elements are meticulously balanced to ensure that the resulting steel possesses the requisite microscopic grain structure to withstand the immense hydrostatic pressures encountered within a rotating bearing assembly. The procurement phase involves the arrival of massive coils of hot-rolled wire rod at the manufacturing facility, where each batch is subjected to a comprehensive spectroscopic analysis to verify its chemical conformity and the absence of non-metallic inclusions that could serve as points of structural failure. The initial stage of processing involves the systematic preparation of the wire rod through a sequence of mechanical and chemical cleaning operations. The hot-rolled surface of the wire is often covered in a layer of iron oxide scale, which must be removed to prevent contamination of the forming dies. This is achieved through acid pickling, where the wire is submerged in a controlled concentration of sulfuric or hydrochloric acid, followed by a neutralization rinse and the application of a thin layer of zinc phosphate or lime. This coating serves as a technical carrier for the industrial lubricants required in the subsequent cold drawing stage. The wire is then pulled through a series of tungsten carbide drawing dies to achieve a precise and uniform diameter. This reduction in cross-sectional area not only establishes the volumetric consistency required for the forming process, but also induces a degree of work hardening, enhancing the tensile strength of the metallic substrate. Before the wire can be subjected to the intense mechanical stresses of cold heading, it must often undergo a process of spherodize annealing. This thermal treatment is conducted within a controlled atmosphere furnace to prevent decarburization, a condition where carbon is lost from the surface of the steel, leading to a soft and structurally inferior outer layer. The annealing cycle involves heating the steel to a temperature just below its critical point and maintaining it for an extended duration, typically lasting several hours. This allows the lamellar perlite structure of the steel to transform into a matrix of spheroidal carbides. This specific microstructure is essential for maximizing the ductility of the steel, allowing it to flow plastically into the hemispherical dies without the formation of internal fractures or surface cracks. The sound of the annealing department is a persistent, low-frequency hum produced by the circulation of inert gases and the steady operation of the thermal control systems. The cold heading process represents the primary mechanical event where the wire is transformed into a spherical geometry. This occurs within a high-speed, horizontally reciprocating press known as a cold header. The wire is fed into the machine at a constant velocity, where a precision-timed shearing mechanism cuts a cylindrical segment of the metal, known as a slug. The volume of this slug is calculated with absolute precision to match the final volume of the ball, plus a small surplus for the subsequent grinding operations. The slug is immediately captured by a transfer mechanism and positioned between two hemispherical dies. As the press completes its forward stroke, it exerts hundreds of tons of pressure, forcing the cold steel to flow into the die cavities. The physics of this deformation are governed by the principle of volumetric displacement, where the metal expands radially until it fills the hemispherical voids. During the cold heading operation, a small amount of excess metal is forced out through the narrow gap between the two die faces, forming a characteristic equatorial ridge known as a flash or a burr. The presence of this flash is a necessary technical byproduct of the forming process, ensuring that the die cavities are completely filled and that the internal grain flow of the steel follows the spherical contour of the ball. The internal grain structure of a cold-headed ball is significantly superior to a ball manufactured through machining, as the fibers of the metal are deformed rather than cut, resulting in a continuous structural matrix that is highly resistant to surface pitting and spalling. The sound of the cold heading department is a dense rhythmic clattering, the sound of thousands of slugs being sheared and struck every minute, forming the fundamental acoustic signature of the facility. Following the formation of the rough spheres, the balls are transported to the flashing or rough grinding department. At this stage, the balls are still characterized by the presence of the equatorial ring and a degree of dimensional irregularity. The flashing process utilizes a specialized machine consisting of two heavy-duty cast iron plates, one of which is stationary while the other rotates at a high velocity. These plates are equipped with a series of concentric V-shaped grooves. The balls are introduced into these grooves and are subjected to a combination of high pressure and abrasive friction as they circulate between the plates. This mechanical action systematically grinds away the equatorial flash and begins to establish the basic spherical geometry of the unit. The sound in this area is a constant grinding drone, produced by the friction of the steel against the cast iron and the movement of the balls through the recirculation system. The logic of the flashing process is one of gradual refinement. As the balls circulate, they are constantly changing their orientation and their relative position within the grooves, ensuring that the grinding action is applied uniformly across the entire surface area. This statistical process of random orientation is what allows the machine to produce thousands of nearly identical spheres simultaneously. A specialized coolant and lubricant mixture is continuously circulated through the grinding plates to manage the thermal energy generated by the friction and to carry away the microscopic metallic fines. This fluid is filtered through a high-capacity magnetic separator to remove the steel particles, maintaining the purity of the lubricant and protecting the surface finish of the balls. The environment of the facility at this terminal stage of the first chapter is characterized by the steady, unvarying rhythm of the flashing plates and the persistent hum of the filtration systems. The steel spheres, while still rough and unpolished, have now achieved their fundamental spherical identity, marking the completion of the initial mechanical deformation sequence. As the balls emerge from the flashing machine, they are cleaned and prepared for the next critical stage of the manufacturing cycle, heat treatment. The metal has been work-hardened by the cold drawing and cold heading processes and must now be subjected to a series of thermal transformations to achieve the final hardness and structural stability required for a precision bearing. The transition from the mechanical domain of the press and the grinding plate to the thermodynamic domain of the furnace is the next logical step in this industrial evolution. The raw wire that began as a monolithic coil has been systematically divided and reshaped into thousands of individual technical units, each possessing the internal grain structure and volumetric accuracy necessary for the high-precision refinement that follows. The emergence of the rough ground spheres from the flashing department represents the conclusion of the primary mechanical shaping phase and the initiation of the critical thermodynamic transformation sequence. At this juncture, the balls possess the fundamental spherical geometry, yet their internal metallurgical structure remains in a relatively soft and unstable state, characterized by the presence of spheroidized carbides within a ferritic matrix. To achieve the extreme levels of hardness, wear resistance, and structural stability required for high-speed rolling contact, the metallic substrate must undergo a rigorous heat treatment process. This involves a precisely controlled cycle of neutral hardening, rapid quenching, and subsequent tempering. The objective is to transform the existing crystal lattice into a fine-grained martensitic structure while ensuring a uniform distribution of residual carbides. This transformation occurs within a continuous mesh belt system, an environment defined by the intense radiance of high-temperature heating elements and the steady, low-frequency hum of the atmosphere circulation fans. The hardening process begins with the automated loading of the steel spheres into the intake of the hardening furnace. The movement of the balls is managed by a vibrating feeder that ensures a uniform distribution across the width of the heat-resistant alloy mesh belt. As the belt advances at a precisely calibrated velocity, the containers enter the preheating zone, where the temperature is gradually increased to prevent thermal shock and minimize the risk of internal distortion. The atmosphere within the furnace is of paramount technical importance. It is a neutral protective environment typically consisting of a blend of nitrogen, methanol, and carbon monoxide. This gas mixture is continuously monitored and adjusted by a computerized carbon potential control system utilizing an oxygen probe. The goal is to maintain an atmosphere that is in chemical equilibrium with the carbon content of the 52100 steel, effectively preventing both oxidation and decarbonization. If the carbon potential were to drop below the specified level, carbon atoms would migrate from the surface of the balls, resulting in a soft skin that would compromise the bearing's performance. Conversely, an excessive carbon potential would lead to the formation of brittle surface carbides. As the balls progress into the primary heating zone, they reach the critical austenitizing temperature, which is typically maintained between 820 and 860 degrees Celsius. At this thermal threshold, the iron atoms within the steel rearrange themselves from a body-centered cubic lattice into a face-centered cubic structure known as austenite. Simultaneously, the spheroidized carbides begin to dissolve into the austenitic matrix, allowing the carbon atoms to take up interstitial positions within the lattice. The duration of this soaking phase is calculated with extreme precision, ensuring that the temperature is uniform from the surface to the core of every individual sphere, and that the carbon dissolution is complete without inducing excessive grain growth. The maintenance of a fine grain size is essential for the eventual toughness and fatigue resistance of the bearing. The environment within the furnace is one of absolute thermodynamic discipline, where the movement of the belt and the flow of the protective gases are synchronized to achieve a perfectly repeatable metallurgical outcome. The transition from the austenitizing zone to the quench tank represents the most violent and critical event in the heat treatment cycle. As the belt reaches the terminal end of the furnace, the red-hot spheres are discharged directly into a deep reservoir of specialized quenching oil. This oil is maintained at a constant temperature, typically between 40 and 80 degrees Celsius, and is subjected to high-velocity agitation by a series of submerged pumps. The rapid cooling of the steel prevents the carbon atoms from migrating out of their interstitial positions, effectively trapping them within the lattice as it attempts to revert to a body-centered tetragonal configuration, known as martensite. The martensitic transformation is a diffusionless process that results in a dramatic increase in the hardness of the steel, typically reaching values between 62 and 66 on the Rockwell C scale. The sound of the quenching department is a persistent metallic clinking as the balls fall into the oil, followed by the deep atmospheric rumble of the oil filtration and cooling systems. The newly formed martensite is exceptionally hard, but it is also extremely brittle and possesses high levels of internal stress due to the lattice distortion. In this as-quenched state, the balls are susceptible to spontaneous cracking and lack the toughness required for industrial application. To rectify this, they must immediately proceed to the tempering furnace. The tempering process involves reheating the balls to a much lower temperature, usually between 150 and 200 degrees Celsius, and maintaining this level for several hours. This thermal energy allows for a partial relaxation of the distorted lattice and the precipitation of fine secondary carbides. The result is tempered martensite, a microstructure that retains high levels of hardness while significantly increasing the toughness and dimensional stability of the steel. The tempering cycle is repeated if necessary to ensure the total conversion of any retained austenite, as the presence of unstable austenite could lead to unpredictable dimensional changes during the service life of the bearing. Following the completion of the tempering cycle, the spheres are cooled to ambient temperature and subjected to a rigorous metallurgical inspection. Samples from every batch are selected for hardness testing, which is performed with a diamond indenter in a Rockwell C-scale verification module. The results must fall within a narrow technical range, typically between 60 and 64 Rockwell C, with a maximum variation of only 1 or 2 points across the entire batch. Additionally, the balls are sectioned and polished for microscopic analysis to verify the grain size, the carbide distribution, and the absence of decarbonization or quench cracks. This level of technical scrutiny is a fundamental requirement of the manufacturing logic, ensuring that the thermodynamic transformations have been executed with absolute consistency. The sound of the inspection area is a quiet, rhythmic clicking of the automated hardness testers and the soft whirring of the polishing equipment. The state of the steel spheres at the conclusion of this second chapter is one of functional maturity. The metallurgical identity of the 52100 alloy has been fully realized through the application of thermodynamic force. The balls are now characterized by a dense, fine-grained martensitic structure with a uniform distribution of hard chromium carbides, providing the ultimate foundation for high-speed rotation and heavy-duty load-bearing. They have survived the intense radiance of the hardening furnace, the thermal shock of the quench, and the stabilizing discipline of the tempering oven. They are no longer soft, malleable forms. They are hardened technical units, ready for the exhaustive mechanical refinement that will eventually render them into high-precision industrial components. The steady hum of the heat treatment facility and the rhythmic movement of the mesh belts remain the constant acoustic backdrop to this industrial evolution, a testament to the precision required to manipulate the molecular structure of steel. The movement of the hardened balls continues toward the next department, where the surface finish and dimensional accuracy will be refined through a sequence of high-precision grinding operations. The logic of the process remains unyielding, a continuous progression from raw material to a calibrated technical instrument. The transition from the thermodynamic domain of heat treatment to the mechanical domain of precision finishing is the next logical step in this industrial journey. Each ball, verified for hardness and structural integrity, represents a successful triumph of metallurgical engineering, a standardized solution for the management of friction and the support of rotation, manufactured with a degree of consistency that ensures reliability across billions of individual units. The movement of the hardened steel spheres into the precision grinding department marks the initiation of the most intensive material removal phase within the manufacturing cycle of high-precision ball bearings. At this terminal point of the thermodynamic sequence, the spheres possess the requisite internal martensitic structure, but their exterior surfaces are characterized by a dark oxidized layer of heat treatment scale and a degree of geometric distortion induced by the rapid thermal contraction of the quenching process. To transform these rough, hardened units into calibrated technical instruments, they must be subjected to a sequence of hard grinding operations. This process is governed by the principles of abrasive attrition and occurs within specialized horizontal plate grinding modules. The environment of this department is defined by the persistent high-frequency drone of rotating machinery, the steady rhythmic splashing of abrasive slurries, and the sterile metallic scent of filtered coolant. The objective of this phase is to systematically reduce the diameter of the spheres toward their final specification, while simultaneously establishing a level of sphericity measured in the tens of microns. The hard grinding machine is a massive, rigid assembly designed to withstand the immense mechanical forces required to abrade the tempered martensite of the 52,100 steel. The core of the machine consists of two horizontal plates, typically manufactured from specialized cast iron or hardened tool steel, which are mounted on a heavy-duty spindle and frame. These plates are equipped with a series of concentric V-shaped grooves that serve as the tracks for the moving spheres. During operation, the lower plate remains stationary while the upper plate rotates at a constant, precisely calibrated velocity. The balls are introduced into the grooves in a dense, continuous stream, where they are captured between the two surfaces and subjected to a combination of high vertical pressure and lateral friction. The logic of this mechanical arrangement is to force the balls to roll and slide simultaneously, ensuring that every point on the spherical surface makes contact with the grinding media in a statistically random pattern. The abrasive intervention is achieved through the continuous circulation of a grinding slurry, which consists of a liquid carrier, typically a water-soluble oil or a synthetic lubricant, and a suspension of abrasive grains. These grains are usually composed of aluminum oxide or silicon carbide, selected for their superior hardness and their ability to maintain sharp cutting edges under extreme pressure. As the slurry is pumped through the grinding zone, the abrasive grains are trapped between the steel spheres and the cast iron plates. The vertical load applied by the upper plate, which is managed by a high-precision hydraulic or pneumatic system, forces the abrasive grains to penetrate the surface of the hardened steel. Through a process of microscopic shearing and mechanical abrasion, the grains remove the oxidized scale and the irregular surface peaks, gradually refining the geometry of the sphere. The movement of the slurry is a critical variable. It must be maintained at a constant flow rate and temperature to ensure the efficient removal of metallic fines and to prevent the accumulation of thermal energy that could lead to surface burns or localized structural changes. The physics of the hard grinding process are characterized by a phenomenon known as randomized contact distribution. Because the balls are free to rotate around any axis as they move through the concentric grooves, the abrasive action is applied uniformly across the entire three-dimensional surface of the unit. This randomized movement is essential for correcting the non-spherical distortions produced during the cold heading and heat treatment phases. If a ball possesses a major and minor axis, the abrasive action will naturally concentrate on the areas of greater diameter, gradually reducing the eccentricity until a near-perfect spherical geometry is achieved. The technical oversight of this process involves the continuous monitoring of the diameter variation per lot and the sphericity, which are verified through the periodic extraction of samples for analysis in a metrology laboratory. The sound of the grinding department is a dense, immersive wall of noise, a combination of the low-frequency rumble of the spindles and the high-pitched hiss of the abrasive slurry as it is projected against the moving plates. A critical component of the grinding logic is the recirculation system that manages the movement of the balls between the grinding plates and the external storage reservoir. As the balls exit the grooves at the perimeter of the plates, they are directed into a collection chute and transported by a specialized elevator or conveyor back to a central hopper. This continuous loop ensures that the entire batch is processed as a singular technical unit, preventing the development of diameter variations between individual balls. As the balls pass through the external section of the loop, they are often subjected to a cleaning or rinsing operation to remove the accumulated metallic debris and spent abrasive before they re-enter the grinding zone. The filtration of the grinding slurry is equally important. It is routed through a series of magnetic separators and high-capacity centrifugal filters to remove the steel particles, ensuring that the abrasive action remains consistent and that the surface finish of the balls is not compromised by the presence of large contaminants. The management of thermal energy during hard grinding is a paramount technical challenge. The friction between the abrasive grains, the cast iron plates, and the martensitic steel generates significant amounts of heat, which can cause the balls to expand and alter the precision of the grinding operation. To mitigate this, the machine is equipped with a high-capacity cooling system that stabilizes the temperature of the grinding plates and the circulating slurry. The thermal equilibrium of the system is monitored by a network of electronic sensors that transmit data to a centralized control unit, which adjusts the cooling flow in real time. This stability is essential for maintaining the dimensional tolerances of the spheres, as even a minor fluctuation in temperature can lead to a variation in the final diameter of several microns. The environment within the facility at this stage is one of constant motion and calculated precision, where the unyielding logic of the grinding machine transforms the rough metallic units into calibrated industrial spheres. As the hard grinding process approaches its terminal phase, the vertical pressure and the concentration of the abrasive slurry are often reduced to achieve a finer surface finish. The objective transitions from rapid material removal to the establishment of the final geometric accuracy. The balls are now characterized by a smooth, gray, matte finish and a spherical tolerance that is significantly improved compared to the flashing stage. The total duration of the hard grinding cycle is determined by the starting diameter of the spheres and the specific requirements of the final bearing grade, often lasting for several hours of continuous operation. The technical verification at the conclusion of this chapter involves the exhaustive measurement of a statistical sample of the balls, utilizing high-precision electronic comparators and roundness testing equipment. The results must confirm that the diameter is uniform across the entire batch and that the sphericity falls within the predetermined technical range. The state of the steel spheres at the conclusion of this third chapter is one of geometric and dimensional readiness. They have survived the intense mechanical abrasion of the grinding plates and the thermal stresses of the friction-heavy environment. The oxidized scale has been entirely removed, and the fundamental spherical geometry has been established with a high degree of precision. The balls are no longer rough, hardened forms. They are now calibrated technical units possessing the uniform diameter and the structural integrity necessary for the final stages of refinement. The steady drone of the grinding department and the rhythmic splashing of the slurry remain the constant acoustic backdrop to this industrial evolution, a testament to the precision required to manipulate hardened steel through abrasive force. The movement of the balls continues toward the next department where the surface finish will be further refined through a sequence of lapping and polishing. The transition from the aggressive material removal of hard grinding to the microscopic refinement of lapping is the next logical step in this industrial journey. Each ball, verified for its diameter and sphericity, represents a successful triumph of mechanical engineering, a standardized solution for the management of load and the reduction of friction, manufactured with a degree of consistency that ensures reliability across billions of individual units. The logic of the process remains unyielding, a continuous progression from raw material to a calibrated technical instrument. The transition of the hardened and ground steel spheres into the lapping department represents the final and most delicate phase of material modification in the manufacturing of high-precision ball bearings. While the previous hard grinding stage established the primary spherical geometry and dimensional consistency, the resulting surface remains characterized by a matte, microscopically irregular finish unsuitable for high-velocity rotation. To achieve the sub-micron levels of surface smoothness and the ultimate dimensional accuracy required for specialized industrial applications, the spheres must undergo the lapping process. This operation is a study in controlled abrasive interaction, where the mechanical force is reduced and the precision of the abrasive media is significantly increased. The environment within the lapping department is one of clinical cleanliness and absolute mechanical discipline, defined by the low-frequency hum of high-torque electric motors, the rhythmic oscillation of the recirculation systems, and the heavy oleaginous scent of the specialized lapping compounds. The lapping machine, while structurally similar to the hard grinding module, operates at significantly lower rotational velocities and utilizes different materials for the interface plates. The plates in a lapping carousel are typically manufactured from a specialized soft cast iron or a high-purity lead alloy, selected for their ability to allow the abrasive grains to become partially embedded within the plate's surface. This embedding of the abrasive transforms the plate into a precision cutting tool, where the individual grains are held in a fixed orientation relative to the moving spheres. The balls are introduced into the concentric V-shaped grooves of the plates in a dense synchronized mass. The upper plate is then lowered, and a precisely calibrated vertical load is applied via a pneumatic or hydraulic manifold. The logic of this mechanical arrangement is to facilitate a three-dimensional rolling motion that ensures the entire surface area of every sphere is subjected to the microscopic abrasive action in a statistically uniform manner. The abrasive medium utilized in lapping is a specialized compound known as a lapping paste or slurry. This compound consists of a liquid carrier, usually a high-viscosity mineral oil or a synthetic glycol-based fluid, and a suspension of ultra-fine abrasive particles. These particles are typically composed of diamond dust, boron carbide, or high-purity aluminum oxide, with grain sizes measured in the single digits of microns. The concentration and viscosity of the lapping paste are monitored with extreme technical oversight, as the fluid must maintain enough thickness to prevent direct metal-to-metal contact between the spheres and the plates, while allowing the abrasive grains to perform their cutting action. As the plates rotate, the abrasive grains act as microscopic chisels, shearing away the peaks of the surface irregularities left by the hard grinding process. This gradual removal of material is measured not in millimeters, but in fractions of a micron per hour of operation. The physics of the lapping process involve a complex interplay between the abrasive grains, the soft cast iron plates, and the hardened martensitic steel of the 52,100 spheres. As the balls roll through the grooves, the abrasive grains that are embedded in the plates scratch the surface of the spheres, while the grains suspended in the liquid carrier provide a secondary polishing action. This dual action mechanism is essential for achieving an arithmetical mean, or RA value, that is virtually undetectable to the human eye. The randomized contact distribution ensures that any remaining eccentricity or non-spherical distortion is systematically reduced. The technical objective of this phase is to achieve a surface finish that is essentially a mirror-like reflection, reducing the coefficient of friction to its theoretical minimum to ensure the longevity of the bearing under high-load conditions. The management of the lapping environment requires absolute stability in terms of temperature and pressure. The friction generated by the rolling spheres, though significantly lower than in the grinding phase, still produces a measurable amount of thermal energy. To prevent the balls from expanding, an event that would alter the precision of the diameter reduction, the lapping machine is equipped with a high-capacity heat exchanger that maintains the temperature of the plates and the slurry to within a fraction of a degree. A network of electronic sensors continuously monitors the vertical pressure and the rotational torque, transmitting the data to a centralized control system that makes real-time adjustments to the machine's parameters. This stability is a fundamental requirement of the manufacturing logic, ensuring that the entire batch of thousands of spheres reaches the final specification at exactly the same moment. The recirculation of the spheres through the lapping grooves is managed by a specialized elevator or transfer ring system. As the balls reach the exit point of the concentric grooves, they are lifted and transported back to the intake reservoir, where they are once again organized into the single file stream. This continuous loop ensures that every ball in the batch spends an identical amount of time under the influence of the lapping plates. During the transit phase, the spheres are often passed through a cleaning module, where a high-pressure jet of filtered solvent removes the spent lapping paste and the microscopic metallic fines. This cleaning is critical for preventing the accumulation of debris that could cause surface scratching or scoring. The filtration system for the lapping slurry is of a much higher specification than that used in grinding, utilizing sub-micron membrane filters to ensure the absolute purity of the abrasive medium. As the lapping process reaches its terminal phase, the vertical load on the plates is gradually decreased and the concentration of the lapping slurry may be further diluted. This transition marks the shift from material removal to surface honing or superfinishing. At this stage, the spheres have achieved their final diameter under highest level of geometric perfection. The sphericity of the units is verified using high-precision roundness testing instruments that utilize a diamond-tipped stylus to map the surface profile in 3 dimensions. The results are analyzed using computer-aided metrology to ensure that the variation from a perfect sphere is less than 0.1 microns for the highest bearing grades. The sound of the lapping department at this stage is a nearly silent rhythmic whisper, reflecting the extreme delicacy of the mechanical interaction. The final sequence of the lapping chapter involves the exhaustive cleaning and protection of the finished spheres. Once the technical specifications have been achieved, the balls are removed from the machine and subjected to a multi-stage ultrasonic cleaning process. This involves submerging the spheres in a series of tanks filled with specialized degreasing agents and deionized water, where high-frequency sound waves create microscopic cavitation bubbles that strip away any residual oil or abrasive grains from the surface. Following the cleaning, the balls are dried in a vacuum chamber and immediately coated with a thin layer of high-purity rust-preventative oil. This oil is essential for protecting the ultra-smooth surface from atmospheric oxidation, which could occur within minutes given the high surface energy of the polished steel. The state of the steel spheres at the conclusion of this fourth chapter is one of technical perfection. The metallurgical journey that began as a raw wire rod and progressed through the intense heat of the furnace and the aggressive abrasion of the grinding department has reached its functional climax. The spheres are now characterized by a mirror-like surface finish, a perfectly uniform diameter, and a spherical geometry that represents the limit of modern mechanical engineering. They are no longer merely hardened steel units, they are precision-calibrated technical instruments ready to be integrated into a bearing assembly. The steady hum of the ultrasonic cleaners and the quiet, sterile atmosphere of the clean room remain the constant acoustic backdrop to this industrial evolution, a testament to the absolute consistency required to manufacture billions of identical components. The balls are now physically complete, but they must be systematically categorized through a process known as grading. This ensures that every bearing assembly consists of balls that are identical in diameter to within a fraction of a micron. This transition from the domain of mechanical refinement to the domain of precision metrological sorting is the final sequence in the industrial life cycle of the progression of the mirror-polished steel spheres from the ultrasonic cleaning station into the metrology and grading department represents the transition from individual component refinement to the final structural integration of the bearing assembly. At this stage, while the balls are geometrically perfect and physically complete, they possess microscopic variations in diameter that are inherent to any mass production process. To ensure that the final bearing operates with the specified internal clearance, a critical factor for heat dissipation and rotational longevity, the balls must be systematically categorized through the process of automated grading. This involves the use of high-sensitivity electronic comparators that measure each sphere to within a fraction of a micron. The environment of this department is an ultra-clean, climate-controlled laboratory where the temperature is maintained at exactly 20 degrees Celsius and the humidity is strictly regulated to prevent any thermal expansion or moisture-induced surface degradation of the 52,100 steel. The grading machine is a masterpiece of high-speed metrological engineering designed to process thousands of units per hour with absolute accuracy. The balls are introduced into a vibratory bowl feeder that organizes them into a single file stream, moving them toward the measurement station via gravity-fed precision ground tracks. The heart of the machine is the measuring head, which typically utilizes a linear variable differential transformer, or LVDT. This sensor consists of a primary coil and two secondary coils surrounding a movable ferromagnetic core. As each ball passes through the measurement zone, it makes momentary contact with a diamond-tipped stylus connected to the core. The displacement of the stylus, caused by the diameter of the ball, alters the magnetic flux within the coils, generating a voltage variation that is proportional to the dimensional deviation from a master gauge. The logic of this system is to convert a mechanical dimension into a digital signal that can be processed at high velocities. The sorting mechanism follows the measurement with synchronized precision. Based on the signal from the LVDT, a high-speed pneumatic gate or a rotating distributor arm directs the ball into one of several dozen collection bins. Each bin represents a specific grade or group defined by a narrow diameter range. For example, a batch of balls with a nominal diameter of 10 millimeters might be sorted into groups with increments of only 0.5 microns. The zero group contains balls that are exactly the nominal size, while the +1 group contains balls that are 0.5 microns larger, and the -1 group contains those that are 0.5 microns smaller. This granular categorization allows the manufacturer to utilize the entire production volume while maintaining the highest levels of assembly precision. The sound of the grading department is a rhythmic, high-frequency tapping, the sound of individual spheres striking the collection bins in a continuous rapid-fire sequence. Parallel to the grading of the balls, the inner and outer bearing rings, also known as races, are undergoing their final preparations. These rings are manufactured through a separate sequence of forging, turning, heat treatment, and precision grinding. The most critical features of the rings are the raceways, the curved tracks where the balls will roll. These raceways must be ground and lapped to a surface finish and geometric tolerance that matches the perfection of the spheres themselves. Before assembly, the raceways of both the inner and outer rings are measured using automated electronic gauges. The data from these measurements is then fed into a centralized assembly control system, which applies the principle of selective assembly. This involves matching a specific set of rings with a specific grade of balls to achieve the exact internal radial clearance required for the final bearing grade. The internal clearance of a bearing, often designated by codes such as C2, C3, or C4, is the total distance that one bearing ring can be moved relative to the other in the radial or axial direction. If the clearance is too small, the bearing will generate excessive heat and fail prematurely. If it is too large, the bearing will exhibit vibration and reduced load capacity. By selecting balls that are slightly larger or smaller than the nominal size, the manufacturer can compensate for the microscopic variations in the raceway diameters. This logic ensures that every assembled bearing meets its technical specification, regardless of the minute tolerances of its individual components. The environment of the assembly area is one of absolute sterile discipline, as even a single particle of dust trapped within the bearing could lead to catastrophic failure. The assembly event begins with the positioning of the inner ring inside the outer ring. The rings are eccentric to one another, creating a crescent-shaped space into which the required number of balls is introduced. Once the balls are in place, the inner ring is centered and the balls are distributed evenly around the perimeter of the raceways. To prevent the balls from making contact with one another, which would cause friction and wear, a component known as the cage or retainer is installed. The cage is a structural frame that maintains the precise spacing between the spheres. It can be manufactured from pressed steel, machined brass, or high-performance synthetic polymers like glass fiber reinforced nylon. The cage is typically installed in two halves, which are then snapped together or permanently joined using a precision riveting process. Once the mechanical structure is complete, the bearing moves toward the lubrication and sealing station. The choice of lubricant is a study in rheology, the science of the flow of matter. For high-speed applications, a specialized synthetic grease consisting of a base oil, a thickener such as lithium soap, and various antioxidant and anti-wear additives is injected into the bearing cavity. The volume of grease is calculated with extreme precision, typically occupying between 30 and 50% of the internal free space. Following the lubrication, the bearing is fitted with shields or seals. Shields are metallic plates that provide a non-contact barrier against large contaminants, while seals are made of reinforced nitrile rubber that makes contact with the inner ring to provide a hermetic barrier against moisture and fine dust. The installation of the seals is a decisive mechanical press fit that marks the conclusion of the bearing's structural synthesis. The final sequence of the manufacturing cycle is the exhaustive performance verification. Every assembled bearing is placed on a specialized testing machine known as an anderometer or a vibration analyzer. The bearing is rotated at a constant speed under a specific load, while a high-sensitivity transducer monitors the acoustic and vibrational signature of the rotation. Any irregularity in the balls, the raceways, or the lubrication will manifest as a specific frequency spike in the vibration spectrum. The bearing is also checked for its starting torque and its radial and axial runout. Only after passing these electronic scrutiny tests is the bearing laser etched with its part number, manufacturer's code, and date of production. The sound of the testing area is a low melodic whirring, the sound of perfectly balanced components rotating in a state of frictionless harmony. The state of the 52,100 steel at the conclusion of this fifth chapter is one of total functional realization. The spheres that began as raw wire rod have been transformed through heat, pressure, and abrasive force into the core of a high-precision mechanical system. The bearing is now a finished technical product, ready to be packaged in vapor corrosion inhibitor paper and shipped to its final industrial destination. The logic of the process is complete. The individual identities of the balls and rings have been subsumed into a singular high-performance unit designed to support the rotation of the world's machinery. The steady, quiet hum of the final inspection room and the rhythmic movement of the laser engraver remain the constant acoustic backdrop to this industrial evolution, a testament to the absolute consistency required to manufacture billions of identical components. The bearings are now prepared for logistical distribution. This marks the end of the fabrication history of the steel ball bearing.